So today we're starting chapter 2, and our lesson is on finding square roots and then comparing real numbers. So let's hit our first goal first. So square roots of a number is basically if you take a number and you square it, meaning you're multiplying it by itself, and you get an answer, well then if you wanted to get back to what was that original number that you squared, you would take the square root of that number. So this little check mark looking thing looks kind of like a check mark with a line coming off the top. That is called a radical symbol, and whatever is inside is known as the radicand. Now it's a little bit interesting when we do square roots. They are the inverse of squares. However, we have to be a little bit careful here. So if we're evaluating this expression here, we know that 3 squared equals 9 because 3 times 3 equals 9. So if we were to go in reverse and do the square root of 9, we could get 3 because that's saying what number times itself equaled 9? Well, 3 times 3 equals 9. But it also works with negatives as well. So if we took a -3 and we squared it, that would be like saying -3 times -3, which we know when we multiply a negative by another negative, we end up with a positive answer, which is why it equals +9. So if we think about that backwards and we say the square root of 9, well, it could also technically be -3 then because -3 times -3 was +9. Therefore, all positive real numbers have 2 square roots, a positive version and also a negative square root. So the square root of 9 essentially then equals positive or -3. So we could write it like this, the 3 with that little plus minus symbol in front indicating that it could be both, or you can just write it as 2 separate answers. So taking a look at the example, usually what we do so that we can know which type of answer we're looking for is we would put the symbol in front to indicate which root it is that we want. So for example, this one is saying the positive or negative square root of 36. So that tells me I want both solutions, both the positive and the negative, and you could just write that simply as the positive or -6. If you would like to, you could also write it as 6 and -6 and write it out as 2 separate answers. Now when we go to number 2, this one doesn't have a symbol in front, so that's indicating we just want the primary or the positive root there. So square root of 49 is just simply going to be 7. Number 3 has this negative out front of our radicand, so our radical symbol, so we just want -2. Number 4 then would be -3. Number 5 would just be +5. Number 6 would be positive or -8. Number 7, -9. Number 8, positive or -10. And number 9, -20. Now let's talk about perfect squares for a minute because they're going to be really useful and handy when we're solving some equations and we're using square roots and things like that. Perfect squares are the numbers that are obtained by squaring an integer. So we're going to talk about the term integer in a little bit, but an integer is a positive or negative whole number, kind of like the example I just gave you. We had 3 or -3 being squared to give us the 9. Well, both 3 and -3 are integers. They're not fractions or decimals, but they could be positive or negative. Now, when you square any integer, so 1, 2, 3, 4, 5, 6, and so on, or any negative number or negative integers, so that would be, -1, -2, -3, and so on, you always are going to have a positive answer, and that positive number is known as a perfect square because if you square root it, you're going to get a whole number or an integer. So, for example, if I did 1 squared or -1 squared, I would get 1. If I did 2 squared or -2 squared, I would get 4, and so on. And so this chart is going to take us all the way up to 20 squared, which would equal 400. So this is just a nice little reference for you. So you're familiar with the numbers that when you square root them, you will get an integer. So now example 2, we can also use those perfect squares to approximate the square root answer of numbers that are not perfect squares. So for example, if I wanted to find the square root of 32 and I didn't have a calculator handy, I could say, well, I know that 25 is a perfect square, and the square root of 25 would equal 5. And I know 36 is a perfect square, and the square root of 36 would equal 6, right? And that's because 25 and 36 were both on my perfect square chart here. So if I then need to know, well, what's the square root of 32, and I don't have a calculator, and I just want to approximate this, so we don't need an exact answer. We know if we put this in on the calculator, we get some decimal between 5 and 6, so 5 point something. But if we're going to round it anyway to the nearest integer, right, well, which one would it be closer to, the 5 or the 6? So which number is 32 closer to? Is it closer to the 36, or is it closer to the 25? Well, since it's closer to the 36, then that would mean our rounded answer or approximate answer here would be 6. So let's look at the square root of 103. So we know that the square root of 100 equals 10, and that's pretty close to 103. Now, what about the next perfect square we would get would be 121 because the square root of that is 11. So here's another example. But 103 is much closer to 100. So even though I know my answer is going to be some decimal like 10 point something, if I'm rounding it to the nearest integer, I know it's going to be much closer to 10. Now, number 3, we're going to do the same concept, but then we're just going to put negatives on our answers because we know we're just saying we want the negative root this time, not the positive. So I know that 49 is a perfect square, which does equal 7 if I square root it. And then the number lower than 48, that's a perfect square, would be 36. And the square root of that equals 6. Now in this case, 48 is much closer to 49, so I'm going to guess that my answer is probably going to be 6.9 or something like that, which I would round to 7. But remember, this was a negative, so we want to put the negative on there. And of course, it would round to negative 7. All right, so 350. Now that one I'm not as familiar with in my head, right? Because it's not maybe a number I use frequently. So if I want to look at my chart, I know it's between 324 and 361, those two perfect squares. So 324 and 361. Now I know the square root of 324. If I look at my chart here, if I know this was 20, this would work out to 19, and this one's going to be 18. So we know the square root of that's going to be 18. The square root of 361 would be 19, but I'm looking for the negative square roots here. And 350 is much closer to 361, so that answer would round to negative 19. Okay, 320. 324 is a perfect square, and that equals 18. But then what else is close to 320? All right, well, 289 would be the one that's less than that. 289, and the square root of that is 17, and this time I want both answers. Again, 320 is much closer to 324, so my approximate answer here would be positive or negative 18, because the real answer would probably be like 17.8 or something pretty close to 18. And then finally, in this problem, we have a negative inside the radical symbol. When that happens, this is actually no real solution. Anytime you have a number with a negative inside the radical, it's no real solution. The reason is because there's no number times itself that will give you a negative answer. So it's impossible to take the square root of a negative number, because if you had a negative times a negative, you would still get a positive. So there's nothing times itself that will give you that negative. If you do put this on a calculator, for example, let's say you wanted to do, see if I can do this, the square root of 12, for example. I think I'm going to have to just move myself over there for a second. The square root of 12, we see that there's an answer, but if we do square root of negative 12, Our calculator gives us this message, error, non-real answer, and then we know, okay, that's why, because you can't solve that. All right, so real numbers. Talking about real numbers are numbers that are not imaginary. Now you might be like, what numbers are imaginary? Well, when you move on to Algebra 2, we will discuss imaginary numbers, which are actually going to solve that problem of square rooting a negative, but we'll get to that later on. Now, real numbers are all the other numbers that you've used up till this point. They can include fractions, decimals, radicals, even certain numbers that are symbolic, like pi. They can all be arranged on just a two-dimensional number line. So 0 would be the middle of the number line, right? And that is always known as the origin. And then on this side, you would have your positive numbers. And of course, even though I'm only writing my whole numbers on this side right now, or my integers here, all those fractions and decimals that would fall in between those numbers could be represented on this number line, right? So like, for example, the number pi, which is 3.14, I could put a spot on my number line for that. Or the fraction 3/2, or 1.5, I could put a spot on my number line for that. And then, of course, on the left-hand side of the 0, you would just continue on with all of your negative values like that. So we can see that all our positive numbers, our negative numbers, fractions and decimals, even if you had something like, for example, we know the square root of 4 equals 2, so I could even plot that there on the number line. Now remember, 0 is neither positive nor negative. It's just that neutral value that separates our positives and our negatives from each other. So when we go to graph numbers, real numbers, they can be put somewhere on that number line. So we're starting out with a 0, and I'm just going to put a couple values on here. I know I'm not going to go past a 3, so I'm going to do 1, 2, and 3, and then I'm going to do -1, -2, and -3. So if I want to graph the 1/2, I would know that that's somewhere between 0 and 1 on the positive side. And I could graph that there. If I want to graph -2/3, I'm going to go on the negative side, not -2/3, -2.3. And I know from 0 to -1, then I go to -2, and -2.3 would be a little bit past the -2 on the real number line. So if we look at example 4, we're going to graph -4 and -5 on the number line. Then we'll write two inequalities that compare them. Well, -4 is right here. -5 is right here. Okay, so we can graph all of these on the number line, right? But these are the two that we're discussing. Now, how do I write two different inequalities? Well, the easiest way to write an inequality is to start with your lower number first on the left, your greater number, which on the number line, if you're reading from left to right, will be on the right. And then if you do it that way, your sign will always point to the left and open to the right. And I always kind of imagine it being like if I wrote the word less than, the L, if I just tilt that L a little bit. Okay, so whenever you're writing them in order from left to right, you can just write the sign in that direction, because it should always be pointing towards the negative side and opening up towards the positive side. Now, another way you could write that inequality would be if you put the -4 on the left and the -5 on the right. However, your sign would have to flip because it still has to point to the smaller number or the more negative number and still has to open up towards the larger or greater number. Okay, so ordering real numbers. So when we're going to do this, first of all, I like to kind of look for my greatest value and then my smallest value so that I know my number line will fit those. So I have a 0 in the middle always, and I'm going to go up to +4. So 1, 2, 3, and 4. And then I'm going to go -1, -2, -3, and -4. Okay, so first things first, I'm going to put -2 on the number line, which is going to be right there, and the +4 on the number line. and the 0 on the number line. So now I'm going to go to 1.5, which is going to be, if this is a 1 here and this is a 2, 1.5 would be about halfway between my 1 and my 2. Then I have the 1/2, and 1/2 would be between 0 and 1, about halfway. And then -3/2, which is actually -1.5. So I know I'm going to go negative, and I'm going to be a little bit in between the -1 and the -2. So -3/2 would be right about there. All right, comparing real numbers. In the table at the right shows the low temperatures recorded in Nome, Alaska each day for 5 days in December. Which low temperature reading was the coldest? So all of them are low temperatures. So we're looking for the lowest of the lows, so to speak, and that would be this one right here because it's the most negative. On the number line, it would be the most or the farthest to the left. So this would be the -11 degrees Fahrenheit. Okay, so let's take a look at example B. Now this time we're saying which dates had low temperatures above 10 degrees Fahrenheit. Well, we know if it's above a positive number, we know that these two could not be answers. And then when we look at the remaining choices, which one of those is above or greater than 10 degrees? It would be the 16 degrees Fahrenheit, which takes place on December 20th. All right, so now let's look at our third one. Which dates had low temperatures below -5 degrees Fahrenheit? So we know it's going to have to be a negative because it can't be below -5 unless it's also a negative. So sometimes people look at the 3 and the 2 and they just think, oh, those are below 5, but this is a -5. So it actually would just be these two temperatures here on December 18th and 19th. Okay, and then finally, an important skill to have is to be able to order these real numbers, particularly when they're mixed up into different versions of numbers, for example, some fractions, some decimals. That can get a little bit tricky sometimes. So if you happen to know that this decimal here, 0.5, is 1/2, if you happen to know that 0.3 repeating is 1/3, if you happen to know that 0.25 is really 1/4, then for me, that was pretty easy to convert those into fractions. However, we still have a little bit of an issue here because the denominators of all these fractions are different. So you may still have some difficulty comparing, like, let's say -2/3 and -3/5, or maybe you have difficulty comparing, the 1/3 and the 1/2 or things like that. So typically when that happens, it's best to change them into decimals. Now we already have these three written as decimals. So for these other three, -2/3 is -0.66 repeating if you just divide 2 by 3 on a calculator. 4/4 is simply just the whole number of 1. And then -3/5 is -0.6, and it just stops there. So this helps me a little bit organize them. Now, another thing or strategy you can use is, of course, always look at your negative numbers separately, because sometimes maybe the numbers that are all negative are far enough apart from each other that's easy to differentiate what comes first, second, third, and so forth. So right here, I'm going to, since all my numbers are small numbers in between 1 and 0, that's all I'm going to really put on there as a reference. So I'm going to look at my 3 highlighted ones here, which are all negatives. Now I have a -0.66666, whatever, which would be the farthest from 0. Then I have a -0.6, and then I have this -0.25. So if halfway between the 0 and the -1 is -0.5, then I'm going to put this one here, -0.25, right about there on my number line. Now the remaining two are both going to be more than halfway to the -1, but not quite to the -1. And they're going to be very close together, but I know that the -3/5 is equal to -0.6, and the -2/3 is equal to the -0.6 repeating, so that one's a little bit more to the left. Now I'm going to look at my three positive values. I already know that 4/4 is equal to 1, so I can go ahead and put that there. Then halfway between 0 and 1 is this 0.5. And then a third of the way, which is not quite half, is the 0.333 and so on. Now notice what I did. Whenever you get a problem in algebra, it's typically you want to leave your answer in the form that your question was given to you. If you're even solving an equation and it's a decimal form, then your answer can be in decimal form. If the original is in a fraction form, you want to leave it in a fraction form. So even though I had mixed numbers here, I want to put the final answers in the order that they were given to me. So notice my -2/3 and my -3/5 remained fractions here. The other numbers remain decimals, and my 4/4, I just left it as 4/4. So what is the easiest way to compare the fractions and decimals? It's really kind of up to you. If all of those fractions, I found it easier to convert those into fractions because I happened to know what those decimals were equal to, but then comparing the fractions was a little bit trickier. So it's really going to depend on the numbers and your knowledge on those fractions or decimals. All right, so let's go on to the real numbers. So real numbers are all the numbers that you're learning in algebra and all the numbers you've learned in math up till this point. Until you get into algebra 2, you're not really going to expand into other types of numbers. Now, I kind of think of this as a chronological thing. So the first type of number that you learn when you're like 2, 3, 4 years old, preschool, you're just learning how to kind of count on your fingers and count objects. That's really just natural numbers. And natural numbers is basically counting objects that you can physically see or, attach to something. And that's why 0 is not included in natural numbers because you wouldn't start counting with 0. But that brings us to our next group or category, which is called whole numbers. Now, whole numbers, yes, you can count with them because natural numbers are technically whole numbers. However, whole numbers have kind of more of like, they represent a value of something or the amount of something. So this is why we can have a 0 here because it's representing that something is absent or doesn't have any value. So for instance, if I had 3 cookies and then somebody ate the 3 cookies, I now have 0 cookies. So I have nothing. I have no more left, right? So it just takes the natural numbers one step further. And that's kind of what you do in elementary school. You learn about subtraction and addition, and things can equal up to 0. All right, then you move on to middle school and you learn about integers. And this is including your whole numbers and natural numbers because those are all technically integers as well. But now we're expanding into our negative whole numbers. So with integers, we have our positive whole numbers, but we also have the negative versions of those whole numbers as well. And of course, these continue on in both directions infinitely. Okay. So now that breaks it down. Those 3 categories are pretty simple, but what really gets tricky is rational numbers versus irrational numbers. So all of those numbers we talked about, the natural numbers, the whole numbers, the integers, they're all considered to be rational numbers. And rational numbers consist of all numbers that can be written as or converted to a fraction. Okay, so that's like the official term or definition. So all of your natural numbers, all of your whole numbers, and all of your integers can all be written as a fraction by simply putting them over a 1. So they're all grouped into this rational numbers category. Now, clearly, anything that's obviously written as a fraction, like a 2/3, that's definitely a rational number because it's in fraction form already. We can physically see it, no question about that. When we get to these other versions of numbers like decimals, can 0.5 be written as a fraction? It is. It represents the fraction 1/2, so that would be considered a rational number. Now, I'm going to skip down to this one here for a second. 2.234, remember, to write any terminating decimal as a fraction, you simply take the numbers after the decimal point and put it over either 10, 100, 1,000, or however many zeros to fill in those slots. So like this one here really would have been 5/10, which simplifies to 1/2. This here is 234/1000. I needed 3 zeros, one for each of those digits, and that round or simplifies to 117/500. Now, of course, those are both rational numbers because they're written as a fraction. And notice they're pretty easy to tell because any decimal that stops, or we say terminates, can always be written into a fraction. Even if it had 5 digits, you could put it over 100,000 and reduce it from there. Now, where it gets tricky is these longer decimals that appear to not stop. So when you have these decimals with the dot, dot, dot at the end, right? So those fall into two categories. Some are rational, some are irrational, and it depends on if they can be written as a fraction. Now, 0.33333, it's the same number repeating over and over and over again. That can be written as a fraction. In this case, you might recognize it. It is 1/3. So if you had a fraction maybe like 0.12121212, if it's the same number or numbers being repeated, that can be translated or converted into a fraction, so it would still be rational. And finally, any square root that you can solve and the solution that you get is a rational number, then that radical itself would also be considered rational. And then the last group is the numbers that are not rational, and those are irrational. Now, irrational numbers are numbers that cannot be written as a fraction. They must be decimals that are either non-terminating, so that means they go on forever. That's what the dot, dot, dot's representing. And they're non-repeating, so there's no repeating pattern. And when I say that, I mean it has to be the same thing being repeated over and over. If you change it slightly, it doesn't count. So if you look at this first example here, this one is irrational, right? Because it's just random numbers. It's got this dot, dot, dot at the end. That's the first clue. And there's not the same thing or same couple numbers repeating over and over and over, so it's irrational. Now, if you look at the next example, we have 0.67, but then it changes to 0.667 and then 6667. So because there's a change, it's not the same thing, it's still irrational. It can't be written as a fraction. This one again, of course, 4545, but then it changes 745, then it goes 7845. Again, there's a change in there. It's not repeating the same thing over and over. This one here, 64575, just random, so that's definitely irrational. Noticing all of these are continuing on, none of them are terminating. And then square root of 11, okay, so if it's not a perfect square, it's going to be irrational. So remember we did that first page. Let's say you don't have a calculator to figure this one out. Well, you know square root of 9 is 3, and you know square, and the square root of 16 is 4. So this is probably going to be like 3 point something, right? Either way, as long as it's not a perfect square, you know it's going to be irrational. And then we have some of these special numbers, like pi is a very famous number that you're probably familiar with, and that's approximately equal to 3.14159 and so on. But again, it continues on and on and on, does not have 1 or 2 or 3 set number that's repeating over and over again. So that would also be considered an irrational number. So now we're going to put all these terms into this Venn diagram to kind of help us see the relationship with each other and organize it a little bit. So like I said, this whole chart is going to represent the real numbers because all of the numbers that we're doing are technically real numbers, right? They're not imaginary. Now, first things first, real numbers can be broken into two categories. They must be either rational or irrational. They have to be one or the other, okay? So every number that's real is also either rational or irrational, okay? Now, it's irrational, that's it. It's just an irrational real number. It cannot be classified as anything else. That's it. And these are all of those long, random decimals that go on and on. Okay, now the reason why I'm saying random is because they're not the same number or same two numbers or same three repeating. Okay, now if it's not a long random decimal that goes on, it's a rational number, right? And this includes the fractions, right? So let's say like 2/3 or something. It includes terminating decimals. So that would be like 0.25, something like that. And it also includes repeating decimals, similar to, let's say, 0.121212. So yes, even though that one goes on and on and on, it's rational because it's 1, 2, 1, 2, 1, 2, 1, 2. Now, within the rational category, there's other types of numbers that are also considered rational, but they also have more specific names. So the first one is integers. Okay, integers are rational. They are rational real numbers, but they are also called integers because they're not fractions or decimals. They're just positive or negative whole numbers. Then even more specific than that is your whole numbers. So whole numbers are integers. They're also rational, and they're also real numbers. And then finally, your most specific name is natural numbers. Natural numbers are also whole numbers. They're also integers, and they're also rational real numbers. But these three here, the integers, whole numbers, and natural numbers, they're all rational. None of them can ever be irrational because none of them will ever be a long random decimal that goes on. Okay, so practicing here. The points on the number line below represent rational numbers, which means we can put them on the number line, which is a true statement about points A and B. So it appears that, remember we did that example with the -4 and the -5. If I just look at this, I know that A has to be less than B, right? So it has to be this choice right here. Okay, other things you could do is you could say A is less than the 0, right? Because A is to the left. You could also say 0 is less than B. Those would be acceptable options as well, but they're not available as choices. Okay, number 2. What is the value of the square root of 36 plus -9? Well, square root of 36, we're asking for the principal or positive root here, so we just need 6. And when we add a negative, we're really just subtracting. So you'll notice as we go through Algebra 1 that we don't really do this double sign stuff that you might have done in middle school when you were first learning how to work with integers. We kind of now just like to simplify it to one sign. So whenever you have a positive and a negative right next to each other, we just make it one minus or one negative. And if you have two negatives next to each other, we just make it that plus. So 6 minus 9 would be -3. Name a rational number that could be point C on the number line. So this is one of those where there's many different solutions as long as it's between -1 and -2. So an example could be -1.5, -1.44, -1.327, whatever, -1.333. You know, it doesn't really matter as long as it's something between -1 and -2. So -1 and something. Okay, number 4, which of the following expressions is the greatest? So if we were to put them on the number line, which one would be the farthest to the right? Okay, so first of all, I know it's not going to be a negative number because those are going to be on the left side of the 0. So I just need to look at these two. Now, again, I have a radical and a fraction, and it's a little hard for me to compare them in those formats. So if I go to my calculator and I do 5 divided by 11, I can convert that to this repeating decimal. You see it's 45, 45, 45, and so on. So I'm just going to simplify it 0.45. And now I'm going to put this radical in the calculator, 0.64. So square root of 0.64, and that's 0.8. So notice once I put those both into that decimal form, it was much easier to see which one is larger or the greatest, and it would definitely be this one here. Which expression is not equivalent to 12? Well, 3 times 4 equals 12. The square root of 144 equals 12. 36 divided by 3 equals 12. However, this one, because of that negative inside, there is no real solution for this one. So clearly this one is not equivalent to 12. Name all of the irrational numbers in this set. Okay, so using process of elimination, we know that 0 is a rational number because it's a whole number and it's an integer. -4 is also rational because it's an integer. And we know the definition of rational means it has to be a fraction, so it can't be 3/5. And then the square root of 36 equals 6, so that's also rational. So now let's look at what's left. Now this one here can be written as 63 over 100, which would make it rational. So that's not the option. But this one here, square root of 10, is between these two perfect squares here. So we know it's probably going to be 3.1 or something like that. It's going to be a long, crazy decimal that goes on and on. So we know that that is the irrational number in that set. And that's it for today. See you next time.